everybody. Thank you to everybody who stayed. Welcome to anybody who joined. I get to introduce Ben Taylor. He's working as an interface designer and software developer building educational technology at Grok Learning. And his focus is on improving the learning experience and the user experience of the product. In spare time, he reads a lot of computer science education research. He really does, because he then gives it all to me, which has been made more difficult after graduating from his master's and promptly losing any direct access to journal papers. Now, instead of logging on, he visits the library, ask him for fun facts about ants. His talk is called Running Python on Your Brain Computer. And please welcome Ben. Oh, okay. Sorry, before you clap. He has got too many slides. So that means that his questions today will be answered in the corridor or at lunch. Please welcome Ben.
Hi. So this talk is called Running Python on Your Brain Computer. It's a talk about tracing code. So let's get into it. Just wanted to say, g'day, I'm Ben. Wanted to get a read of the audience. How many people here are teachers? Put your hands up. Great. How many people are interested in education but are not teachers? Awesome. And how many people are students, especially high school students? Cool. Awesome. Great. So I'm Ben. I work at Grok Learning. This is a photo. Oh, sorry. This is us being professional. We mostly teach high school kids to code online. We have a platform for that, but we also help a few universities, and we have some stuff for primary school students, and we also collaborate with the ACA, who are fantastic. Some of my role is about learning, some of it is about technology. So recently I built this thing, which is our new interactive notes for the NCSS Challenge 2018. What it allows is it creates structure to reading for younger students especially, but it also gives feedback and encourages interacting with our notes. And all of our notes are interactive. This is something I built. So let's get into the actual talk about tracing. So just a bit of an introduction. In this talk, I'm going to go through what tracing is, why it's useful, how we learn it, and how we can teach it a bit better. So tracing, if you haven't heard the term before, is simulating the execution of your code to see how it works. And this is the more formal definition of reading code. So simulating rather than reading. And why should we trace? Why is tracing important? So I'm going to give a little bit of an example from the NCSS Challenge this year. The NCSS Challenge is an online programming competition that more than 20,000 people have done around Australia and the world, and it's currently running. This problem is called pizza predicament, and it's an intermediate problem, so aimed at students in years 9 and 10-ish, though we obviously have students in year 7, year 8, year 12, year 3 doing this. In this problem, students are asked to read in a string of characters like HPCM and then print out the ingredients for that pizza. So if the order was HPCM, it would be ham, pepperoni, capsicum, and mushroom. If the order was OMPKHL, it would be onion, mushroom, pepperoni. And then if it doesn't know what that character is, it should say more cheese. So this particular pizza would be a little bit cheesy. It would have a bit of extra cheese. So I'd like to have a look at an imaginary student's attempt at this problem. And this is synthesized from me looking at a few different students and how they approached the problem. So this is Batilda's first attempt. So Batilda has got a lot of for loops, and each of those for loops checks a single letter. And they've marked it, and testing the first example in the question, they got it right. So they feel a bit proud about it. But second example, it did not produce the correct output. And what their eyes are drawn to straight away is that they didn't hit the more cheese part. So they're not printing out more cheese when they get to the letters that are not that they don't know. So Batilda's second attempt, oh no, is cut off down the bottom a little bit, but you can see it. It says, else print more cheese. And when their program runs, their program goes ham, pepperoni, capsicum, more cheese, more cheese, more cheese, mushroom. And this is a very cheesy pizza. And this is unexpected for Batilda. Batilda thought that their code was going to work, but instead their solution doesn't even pass the first test, which they were surprised about. And part of it is because of the way they've used their else statement. So why has Batilda done this? Why have they put their else statement in that particular spot? And it's important to realize that novice learners are just using what they know. If they don't comprehend their own code, they do really strange things to try and fix it. And that's confounded by the bugs that they introduce themselves. So this is Batilda's code. And the big problem really is all the for loops. But the little problem is that extra else statement right at the end. And all of this comes together because this student is a novice tracer. They're not particularly good at reading their own code yet. Part of this is probably that they're interpreting their code like English. So if you read this as English, we might say, look for H in the string. If there's a H, print ham. Look for P. If there's a P, print pepperoni. Look for M. If there's an M, print mushroom. Otherwise, print more cheese. And when you read it like that, it does sound like it solves the problem. But that's not how the computer reads it. The other thing that students will do is apply their own preconceptions about how they think their code works onto the code that they've written. So if they think that their code works, then they're going to expect that it works in a particular way. And this is going to frustrate them. And this is the student that emails us and tells us that our tests are wrong. And that's fine, we'll help them out. But all of this comes together because this student isn't running Python on their brain computer. They're not really simulating it in their head. They're reading it out or they're making other mistakes. So what would an expert tracer do? An expert tracer would behave a little differently. So I've set up how I would diagram tracing in front of students, although I'd probably be using a whiteboard and not this presentation. And what I've got on the right is Batilda's code, and what I've got on the left is a table for variables and an area for output. So we're going to run through this code to have a look at where the bugs are. So we read in order, and it's HPCM. Then we go into the for loop. And the first step of the for loop is setting the letter variable to be H, which is the first character in the string. Then we go into the for loop. We check if the letter is H. It is H. And so we do the if statement, and we print ham out. Then we repeat this process. And it's very important that we repeat this process, because a lot of students will skip this part. They'll just say, well, that's what the for loop does, and they'll move on. So we repeat, and we go P, and we go for the P. If the letter is H, it's not, and so we start again. For letter in order, C. If the letter is H, it's not, we move on. For letter in order, if the letter is H, it's not, and so we move on to the next for loop. Now, I'm not going to put you through the torture of going through the whole example, so let's skip ahead a little. So we've got this last for loop, and this is what I think is the most interesting part of this solution. This student has this final for loop, which creates the more cheese problem, the very cheesy pizza. First step was we set letter in order. If the letter is M, it's not, and so we go to the else statement and print more cheese. We repeat, if the letter is M, it's not, else print more cheese. For letter in order, if the letter is M, it's not, so we print more cheese. And if we do this, if we go through this very painful process of completely simulating the code, the bug becomes so much more visible. The bug is screaming at you that each time that loop happens, the else statement executes and prints out more cheese. Finally, of course, we want to go to finish this program. If the letter is M, it is, we print mushroom. And so this is how we would trace through this program as an expert tracer and not as a novice tracer. And this is the kind of exercise that you can do in a classroom or in a code club or at university tutoring to help students understand what's really going on with their code. And the thing about tracing is that it's really difficult. Students struggle understanding code. They struggle understanding code that they've written themselves. And simulating the execution of code requires a lot of patience and attention to detail. That particular example took quite a while, and I'd structured and drawn it ahead of time. But encouraging students to do this process builds up their confidence with it, and it'll allow them to code and debug more effectively. A big difference with tracing to other skills is that it can be quite invisible. It's hard for you to tell when you're talking to a student whether they're really simulating the code in their head or whether they're just kind of reading it, whether they're doing the English way of reading it. And tracing is important. Comprehension has a big impact on composition. When a student doesn't understand their own code, it's very hard for them to add to it. Debugging code is much harder when you don't understand how your code works. It's harder to spot the bug if you don't see where the bug really is. Finally, it helps with computational thinking, because being able to simulate a computer in your head is kind of the thing about computational thinking. So how can we teach tracing to students? Well, learning tracing happens as students learn to code. If you're not teaching it, students are learning it themselves, just in perhaps not an ideal way. The first steps of learning to trace happen when we start out with variables. So here is an example of a problem on Grok. This is the hello name problem. It says, what is your name? Grok, then it responds with hello Grok. If you were to input Frodo, it would respond with hello Frodo. If you were to input Nikki, it would say hello Nikki. So this is Bonathan's first attempt. He's written input what is your name and then print hello Grok. And this is a really common solution to this problem. Now, this passes a lot of tests because it does get the hello Grok example correct. But when it comes to the next step, and it's got the input of Frodo, it still says hello Grok. So this student reads the feedback, oh, I meant to say hello Frodo. And of course, they implement this program, which says hello to Frodo. Then they don't pass as many tests, and they're like, what's going on? I made it say hello Frodo. And now it's saying hello Grok is the correct answer. So they change it back to hello Grok. And their program gets through the same tests, but then fails again. Of course, the student is now very frustrated. They don't understand what's going wrong. Why don't they understand what's going wrong? Maybe we can explain variables better, and yeah, that's part of it. But they have a fundamental misconception about computers and how they work. They don't quite understand yet that one program can do more than one thing. And that means they don't have in their head a model of computation. They're making hypotheses and testing them, but without the right model, they make strange hypotheses and come up with strange solutions. So what's a computer? A computer is a machine that can solve any problem. We're done. In this case, really, this is a machine that can say hello to anyone. But this idea of a machine that can solve any problem is fundamentally weird. There's no other machines that aren't computers that you interact with that can do this. So often when we teach, we like to teach with metaphors. And the core idea behind tracing is to simulate the machine in our heads, the computer machine, the Python machine. At the simplest level, computers are machines that perform instructions one by one. And so we often use a metaphor like this, which is a recipe. And a recipe, if you mess up the order of instructions, then the recipe doesn't work. If you whisk the jug before you put the eggs in, the recipe is not going to come out the way you expected. So an instruction is a single operation performed by a computer. But a computer is quite different to a recipe. Computers aren't pancakes. And if you compare them, there's a big difference. At the end of a recipe, you always get the same thing. But at the end of a computer program, you can get a different thing, depending on what the input was. And so here's a metaphor that's similar, but uses variables. The first step is to ask, how many people are we serving pancakes to? Then we crack n serves of eggs into a jug, then pour n serves of cups of milk into a jug. And with this example, suddenly we're making a recipe that can solve all of your pancake problems, not just one pancake problem. And this is much more like a computer. It could make pancakes for one person or 100 people. The big difference is state. And state is more formally the context that computation runs in. Usually state means variables. So if we have instructions and state, do we know all about computation? Is this the only model we need? Not quite, but these two things, they're quite important. So let's look at a more complete model. So this is how you might model computation as a student who is tracing. This is an ideal model and probably not the model that your students have. So we have code that the student has written, and this part is separate to what is actually running. This is the code they've written, not the code that's running. And it goes into the machine. The machine is something like Python, an interpreter that runs the code. This part, the machine, is humongous, and it represents everything that Python can do. And if you imagine that machine, that little block, is huge. It's like a TARDIS. Inside is all of Python. And the machine interacts with state. This is the invisible stuff that's stored in memory. And when the machine interacts with state, then we get dynamic behavior. The machine takes in input, which the user has given it, like our example with variables, and it creates output, like hello Nikki. All of this together is in the literature called program dynamics. This is how code, input, state, and the machine interact to create complex dynamic behavior. Program dynamics is a threshold concept, which is a fancy way of saying that it changes the way you think. Once students understand program dynamics, once they have this model in their head, they can't imagine how they thought computers worked before that. And if you have a good model of program dynamics in your head, you may struggle to see how students misunderstand their own code. When we're tracing, students have to run this quite complex model in their head. No wonder it's so hard. If students have to model code going into a machine, the machine executing that code, the machine modifying state and variables, it receiving input, we're going to need a lot of help to get those students able to do that and able to trace as experts and not just as novices. So I've got some practical tips to help students develop their skills in tracing. So first off, we want to encourage doodling and sketching. So this is the same kind of thing that I did in my diagram. You want to get them to do on paper. And this is a great way to get students out of their head. And it's very easy to make mistakes in your head and then not realize you've made a mistake. People are quite confident about their mental capabilities, but when they're exposed on paper, suddenly they realize they were making mistakes. And my other example is tracing diagrams. And this is more just a formal version of sketching. Similar to how I did, my diagram was much more structured, but a student can just do it with a pen and paper. Another thing is doing tracing exercises. So something I often do with students who are struggling with a program is I get them to say out loud to me every step that they think their program goes through. So if they read it out, like we did with our tracing, I can see into their head and see what they think the computer is doing, which is quite important because if they have a misconception, I need to be able to identify that. The other thing is having written tracing exercises. These are common in exams at university, but it doesn't have to necessarily be a university-level difficult problem. Being able to read through some code and come up with what the output is a really important skill. Debugging also typically involves tracing. So debugging code is a great way to practice tracing. It also means that you need to challenge the way you think a program runs. If you give students some code with a subtle bug, They then have to trace through it and find that subtle bug and challenge their own preconceptions about how the code works. Another tip is using explicit instruction. And this is kind of what I've been alluding to with these models of computation. If we teach students a model of computation, and it doesn't necessarily have to be a complete model of computation, it can be something that we slowly build up over time, they can use this model of computation when they're simulating how code works in their head. We can also teach them by doing tracing demonstrations like I did. If you run through code on the board, that will help to scaffold students' own ways of tracing. The final thing I've got here is common structures. And this is a bit difficult. We could probably have another whole talk about this. But things like using a variable to accumulate, or using indexing, or having a minimum value that you retrieve from a list. These are patterns that we use in code often that students don't necessarily know about. And by teaching them explicitly about these common structures, they can then kind of abstract away a little bit and see, this is a case where we're using a loop to accumulate. This is a case where we're using a loop to find the maximum value. So students are going to have a lot of issues when they go through and learn to trace. And one of the biggest issues, as I've kind of spoken about before, is reading in English. Students are familiar with English, and fortunately but unfortunately, Python reads like English. And if students read Python as English, they're going to come up with some really strange ideas about how their code works. And this can be a really big issue with students. One of the most common scenarios I see is students using or and in Python in ways that don't quite make sense because they're used to using those in English. Formally tracing can help break their habit of reading in English. One of the other things that students do, which we all do, is coming up with a theory and then proving it's correct, rather than questioning the theory. And this can be a big problem when tracing code. You need to make sure that students are questioning themselves and their own interpretations of how the code works. And part of this can be jumping into Python and running the line of code, subbing in the values that they think, and then running it. The final thing that they'll do when misinterpreting is skipping steps. And this is a thing that we all do. We think, I understand it, and then skip straight over that bit. And then inevitably, the bug is in the bit you skipped. So they need to trace every single bit. Cognitive load comes into tracing quite heavily and quite quickly. Really, the reason that students are tracing poorly is that they're not able to keep all that stuff in their head. And this is why I talked about sketching. Sketching is an external representation that helps students get their work out of their head and onto paper. So they're not using their working memory to go through and solve problems. They're using the paper to do it. Hitting cognitive load limit, it causes students to make really silly mistakes. A really common one is to think that all the variables are the same value. And this can result in some really strange behavior. And this is because the students just don't quite have space in their working memory to store what the code is doing as well as all the variables. The other thing is that students will become very focused. And this is similar to skipping, but it's a bit more about the fact that they can't keep all of the code in their head at once. They'll focus on a certain area that they've hypothesized is the problematic area or the important area, and they won't think about how the surrounding area of the code may change its behavior. For example, the state may not be what they think it is when it comes into that area. So let's review over what I've talked about so far. Tracing is simulating the execution of your code to see how it works. When we're tracing, students will have a model of computation in their head. Ideally, we want them to have something like this, but it's okay to scaffold it and build it up over time so that they start off with, say, just steps that happen in order, then they add state, and then they start to add more and more parts to this model. We can help students in the classroom by using things like doodling and diagrams. We can do tracing and debugging exercises, and we can teach them explicitly models of computation. And most importantly, what we want our students to do is run Python on their brain computers. It seems like I have time for questions. So if anyone has any questions, Nikki will be roving.
Thank you very much, Ben. Yes. Questions. Surprise questions. Surprise questions for Ben. Surprise questions for all of us.
Oh.
I'm not being 100% serious, but now I'm tempted to ask, is there one of those URLs I can just point students to when I'm tutoring and say, just go and read this computational model and then come back to me and talk about it?
I would like to have some stuff in Grok that supports students to build up their tracing. We don't really have anything like that. But if you have a look, there's a website called Python Tutor, which has you can paste in some code, run it, and it will output something like my tracing diagrams.
Has there been any studies on the best tracing techniques and which ones work well and which ones don't?
So there's a little bit of literature on sketching types. So the one that I used where we cross out values and move on to the next value, that's quite useful. There's also a version which is kind of a bit more rotated where you have variables in columns and you put the new variable down. But mostly it's about making sure that the old value is crossed out and the new value is written there. And that's kind of the theme of what is more effective. If you talk to me after, I can point you at some of the literature. Yeah.
Similarly, are there any websites that have tracing challenges that you can sort of direct people to or challenge yourself on?
Don't know any off the top of my head, but maybe Python Tutor is a good place to start. The Python Tutor has some stuff on tracing, yeah.
Have you encountered any sort of difficulties when people are thinking of things in a sort of more declarative rather than imperative manner, or vice versa, when teaching?
So you mean that they're imagining the computer can kind of understand them a bit more, or what do you mean specifically by declarative, as in?
Yeah, as in people assuming that when they're coding something in Python that it's more declarative than it actually is.
So as in when you declare the value of something, it never changes, or, sorry, I'm not quite sure. Can you give me an example?
Well, actually, that's the sort of thing that
yeah,
I'm getting at.
Yeah, so assuming that a value cannot change over time. Is that what you mean?
Yeah, or that the structure of the computation itself is something that the computer comes up with for you.
Right, I say like SQL would.
Yeah,
okay. Yeah, so this is kind of related. There's a term often called the superbug, which is the student imagining that the computer knows more than it does. And really, this is an issue with students not quite having a model of computation. And I mean, I've encountered it in various forms, and specifically it's the imperative model of computation. And we can bootstrap this by helping them to learn about how the program runs through each step. And getting them to trace really is the solution, is helping them understand that the computer really is that dumb, and it really only does exactly what you tell it to do. Yeah. Yep.
So do you think, like obviously a debugger can do all this tracing thing.
Yep.
So do you think showing students a debugger early would help them because they can see what's going on, or harm them because they don't get the opportunity to do it themselves?
Yeah, that's a good question. I think that you probably need to have at least some practice tracing code before you use a debugger. The other thing with a debugger is that they can be quite complex to use. So I would say it's going to depend on the student, and I don't really know off the top of my head what order is more important there.
Along the same lines, have you thought about putting that type of debugger into Grok Learning, so a tracing simulator?
Yeah, so what we do have is, not many people use it, and I've been meaning to write a blog post on this for ages, is we have a terminal button. And when you press the terminal button, it will run your code, and then right at the very end, it will dump you into a Python interpreter. So it doesn't quite do the same thing. It doesn't allow you to trace, so you can't step through each line of execution, but it does get you to a point where you have the full state of the program, and you can then go and inspect it. So you can type in a variable and press enter, and you see the value of the variable. But yeah, I would love to have some more scaffolding for tracing. Is there any more, Nikki?
There is, but we're out of time.
Okay, cool, fantastic.
But Ben will be around in the various breaks for more questions.
Yep.
And thank you very much for speaking. I keep forgetting. I do
You have
like
a
this thing where I get to mug people. Yes. Thank
you
you very much.
Thank you very much.
Coveted PyCon mug. Yeah.
Thank you, everyone.